Welcome to GenAI Level Up, the podcast where we decode the future of artificial intelligence one breakthrough at a time.
Whether you're just starting your AI journey or you're a seasoned expert, you've come to the right place. Our mission is to make the complex world of generative AI accessible to everyone, everywhere.
In each episode, we dive deep into the foundational concepts, the latest research, and the transformative applications that are shaping our world. It's time to get smarter, faster. Let's level up together.
Okay, let's unpack this. If you spend any time thinking about large language models, the core of modern AI, the computational cost is just staggering.
It really is.
Every query, every bit of text generated, it just eats up massive amounts of energy. And that's not just about money, right? It's becoming a real environmental issue, a logistical headache.
Absolutely is. And when you actually trace that energy drain back to its source, inside the most common LLMs, the transformers, there's one piece that really stands out.
Okay.
It's the bottleneck, especially during inference, when the model's actually doing its thing, generating output.
Right.
That bottleneck is the attention mechanism. More specifically, it's the memory needed for it, the key value cache, the KV cache.
Ah, the KV cache. That's like the model's working memory. Yeah. Storing token projections so it doesn't have to recalculate the whole history for every single new word.
Exactly.
Which is, it's smart for getting accurate results, but it sounds like it's a real killer for speed and power use.
Precisely. And today, we're going deep into some research describing a really radical solution. It's an analog in-memory computing architecture, an IMC architecture.
Analog IMC. Okay, that sounds like a fundamental shift.
It is a complete hardware overhaul specifically designed to tackle that KV cache problem.
Yeah.
So our mission today is to walk you through how this new tech works, why it gets around the basic physics limitations of normal GPUs, and how it pulls off one of the most, frankly, unbelievable performance results we've seen in AI hardware. We're talking an energy reduction of up to 5 orders of magnitude.
Well, hold on. 5 orders of magnitude. That's not just tweaking things. That sounds like changing the game entirely.
It really does.
So let's start with the basics. Why is the current setup using standard GPUs so bad for the KV cache? What's actually happening inside, say, my graphics card that's so wasteful?
Okay, it really boils down to location. And movement. Lots of movement. Imagine you're trying to cook a huge meal, like Thanksgiving dinner. The actual cooking, the computation, that happens on your tiny, super fast stovetop. That's like the SRAM cache right on the GPU chip.
Right, the fast bit.
But all your ingredients, the massive KV cache, they're stored way over in a giant warehouse miles away. That's the slower high bandwidth memory, the HBM, which is usually off chip.
Okay, that's a great analogy. I get it.
So for every single new word the LLM spits out, it needs to fetch potentially gigabits of those ingredients from that distant warehouse. Drag them all the way to the stovetop, use them for maybe a fraction of a second, and then haul everything back again. And that KV cache gets huge. Like for the Mistral 7B model, even a batch size of 1 needs 8 gigabits.
8 gigabits shuttling back and forth for every single token. Wow.
And that constant massive data transfer. It's just incredibly energy expensive.
So the GPU is burning way more energy just moving data around between the slow HBM and the fast SRAM than it spends on the actual math, the attention calculation itself.
That's the key takeaway from the sources, yes. The energy for data access often dwarfs the energy for the computation. In AI inference, memory access is the real power hog.
Right. And we've seen attempts before, like near memory computing, just putting standard memory closer. Why didn't that fully solve it?
Because the attention mechanism is just uniquely demanding. It's really tricky. For LLM inference, you need like 4 things all at once.
Okay, what are they?
You need super high parallelism for speed. You need high density to store long conversations. You need high data retention so the context doesn't just vanish. And you need really fast, low energy writing, because that cache gets updated constantly, every single token.
And regular memory, like DRAM or SRAM.
They just can't deliver that specific mix. You might get 1 or 2, but not all 4 efficiently.
Okay, so we need to actually merge the memory and the computing right into one thing.
Exactly.
Which brings us to this analog solution. And the core tech seems to be these things called gain cells. What exactly are they?
So gain cells are an emerging type of memory device. They change the game in how we store information, Basically, a gain cell holds information as a voltage charge on a tiny capacitor, kind of like DRAM does.
Okay, similar so far.
But, and this is crucial, they have a dedicated read transistor built right in.
And what does that dedicated transistor do for you? What's the benefit?
It allows for non-destructive reads. When you read the data, you're not draining the charge away.
Oh.
Which is absolutely essential for in-memory computing, because you're constantly using that stored data in place to do calculations. These cells are great for this job because they offer high endurance, really low write energy, super fast writing, and importantly, they can store multiple data levels, not just 0 or 1.
Multi-level capability, right. That helps with making things more efficient, like quantization.
Exactly.
And the sources mentioned future versions using OSFETs, oxide semiconductor field effect transistors, using materials like IGZO. That sounds like where the density could get crazy.
Absolutely. OSFETs are a big deal here. They let you do 3D fabrication, stacking memory layers vertically. Plus, their material properties mean they hold their charge much longer, potentially for multiple seconds without power. Yeah. It's a huge improvement over current silicon CMOS cells.
Okay, so we have these efficient, dense memory cells. Now, the computation. The sources say the core attention math dot product, scaling it happens fully in the analog domain.
That's a leap.
Moving from digital zeros and ones to continuous voltages. Why go analog? And what was the biggest challenge they had to solve there?
Well, you go analog because fundamentally analog computation can be incredibly energy efficient. The physics is just different.
Right.
But the biggest hurdle, the thing that often wipes out those savings, is the need for analog to digital converters, ADCs.
Ah, yeah, the translators back to digital.
Exactly. Usually neither to turn the analog result back into digital numbers the rest of the system understands.
Yeah.
And ADCs can be seriously power hungry. They often eat up all the energy you saved by going analog in the first place.
So how did they get around that? How do you avoid the power-hungry translator?
They came up with this really brilliant workaround. They used charge-to-pulse circuits.
Charge-to-pulse?
Yeah. So instead of converting the final analog voltage directly into a digital number using an ADC, the system translates the accumulated charge, the result of the computation, directly into timed, discrete digital pulses, like little clicks.
Okay.
And then simple pulse counters just count those clicks to get the final digital readout. They effectively skip the whole complex, high-precision, power-guzzling ADC step.
That is clever. It's like measuring something with clicks on a counter instead of a high-res digital scale. Very neat. They also had to tweak the algorithm a bit, right? Moving from the standard softmax activation function to ReLU.
Exactly. ReLU, the rectified linear unit, is just mathematically simpler to implement well in analog circuits. It works element-wise, making the hardware design much more straightforward compared to softmax, which involves relationships across all the elements and is tricky to do efficiently in analog.
Makes sense. And one more thing on the architecture. Physical chip size isn't infinite. How do they handle really long conversations or sequences if the on-chip memory is limited?
Yeah, that's where sliding window attention comes into play. It's basically the memory management strategy.
Okay.
It means the hardware only needs to physically store, say, the most recent keys and values right there in its local analog memory. It keeps the chip size practical, while the overall LLM across all its layers can still keep track of context over much longer sequences.
Okay, here's where it gets really interesting for me. You can design this, almost perfect custom analog chip, but then you try to run a standard pre-trained model on it, like GPT-2, and suddenly the real-world physics of the chip causes problems.
The classic hardware-software gap, but amplified by analog quirks. You get this perfect storm of what we call analog non-idealities.
Like what?
Well, first, the math isn't perfectly clean. You get some nonlinear effects in the multiplication within the gain cells, not pure dollar times B. Second, you have pretty strict quantization limits. Inputs might only be 4 bits, the stored value is just 3 bits, the output maybe 5 bits. That's coarse.
Okay, nonlinearity, quantization. What else?
And the third one, arguably the trickiest, is leakage. Capacitor leakage.
Ah, right. You mentioned the time constant. For current silicon cells, it could be around tau equals 5 milliseconds.
Exactly. 5 milliseconds. Think about that. It's like writing on a whiteboard where the ink starts fading significantly after just 5 milliseconds.
Wow.
The stored value, the actual memory of the conversation history held in that KV cache charge, is constantly decaying. It's a physical reality.
Yeah.
So you just can't take a model trained in the perfect digital world and expect it to work when you just drop its weights onto this leaky, slightly nonlinear, quantized analog hardware. It'll fail.
So the hardware alone can't compensate for its own physics. You need a software fix. And this is what led them to the hardware algorithm co-design idea, adapting the software model to the hardware's flaws instead of trying to build physically perfect hardware, which might be impossible or too expensive.
That's exactly the insight. They developed this really clever adaptation algorithm. It takes a pre-trained model, like GPT-2, and essentially fine-tunes it to tolerate the hardware's constraints. And crucially, it does this without having to do the incredibly expensive process of training the whole massive model from scratch directly on this specialized hardware.
Okay, walk us through that. How do you actually teach a model to work with, like fading ink?
It's kind of a neat three-step process. First, they fine-tune an intermediate linear model. This model already has the target quantization baked in, and it uses the ReLU activation, but it doesn't have the nonlinearity or the leakage yet. It's like a stepping stone, a reference point.
Okay, linear reference model first.
Then they transfer those adjusted weights over to the actual hardware model, the one that simulates all the nonlinearities in the decay physics.
Right, but it won't work perfectly yet because of those extra imperfections.
Exactly. So the final step is this iterative adaptation. They use a special scaling algorithm. They adjust these little scalar values, just simple multipliers called ed_n dollars, for the query key and value projection calculations. They keep tweaking these scalars and dollars iteratively until the statistical behavior, like the average output, the spread of the outputs of their non-linear leaky hardware model, closely matches the statistics of that intermediate linear reference model.
So they're nudging the model's internal calculations to compensate statistically for the hardware's weirdness.
Yep.
They're making it expect the leakage and nonlinearity.
You got it. They're essentially programming the model to be robust to the physical imperfections it's running on.
And the big question, did it work? Did this co-design approach maintain the LLM's performance?
It absolutely did. They tested it using Perplexity, that standard benchmark, where lower scores are better, meaning the model is more confident and accurate in its predictions.
Right.
And the adapted analog model achieved Perplexity scores very similar to the original publicly available digitally trained GPT-2 model on standard NLP tasks. The researchers were pretty confident, stating there were no apparent limitations for using this analog approach for these language tasks.
That's huge. It means the complexity of the co-design pays off. You get the hardware benefits without sacrificing the AI's capability.
Precisely.
All right, let's get to the payoff then. We know the hardware concept works. We know the software adaptation works. But the headline grabber was the performance leap. What did the analysis show for speed and energy?
Yeah, the performance numbers are, well, they're pretty eye-watering. Let's start with latency, the speed.
Okay.
The estimated total time for one full attention computation, basically generating one new token, is just 65 nanoseconds.
65 nanoseconds. I mean, that's practically instantaneous for any real-world application.
It's incredibly fast. And the energy side is even more stunning. One attention head processing one token uses an estimated 6.1 nanojoules.
Nanojoules. 6.1. Can you put that into perspective? How little energy is that really?
It's minuscule.
Yeah.
But like you said earlier, maybe compare it to a tiny LED light on your router. That LED probably uses maybe 1 million times more energy than this entire attention calculation in the same amount of time.
Wow. Okay. So how does this stack up against, say, a high-end GPU that people might use today, like an NVIDIA RTX 4090?
All right, the comparison is stark. For latency, this analog IMC approach is up to 2 orders of magnitude faster. That's around a 300 times speed up compared to the 4090 for just the attention part.
300x faster is definitely impressive. But you mentioned 5 orders of magnitude earlier. That must be the energy saving.
That's where the analog advantage really hits home. Compared to that same RTX 4090, the energy reduction is up to 5 orders of magnitude.
5 orders. So that
means it's potentially up to 90,000 times more energy efficient for doing that specific critical attention calculation.
90,000 times.
No.
It's hard to even wrap your head around. More efficient than a top-tier GPU just for fixing that memory bottleneck.
It completely changes the picture.
Yeah, that doesn't just make running LLMs cheaper. It potentially makes them vastly more accessible, right? You could run powerful AI in places you just couldn't before.
And the architecture seems to scale well, too. They use tiling, breaking the big memory arrays into smaller 64 by 64 blocks to handle signal issues like voltage drops. And based on those dense OSFET technology projections, one complete attention head built for GPT-2's specs would only take up about 0.5 square millimeters of chip area.
Half a square millimeter. That's tiny.
Super tiny. That density means you can pack lots of these ultra-efficient units onto a chip for massive parallelism without needing a giant piece of silicon.
Okay. So What does this all mean then? We've seen this combination of new memory tech, the gain cells, and this smart software adaptation, the co-design, managing to solve arguably the biggest energy hog in LLM inference.
Yeah, I think the immediate takeaway for anyone watching this space is that this huge leap in power efficiency for AI, it's not just theoretical anymore.
Right.
This research gives a pretty concrete blueprint. It shows we can use these advanced memory technologies to get absolutely massive energy savings, and critically, without losing the accuracy needed for complex tasks like natural language processing.
But it's important to remember, this study really zoomed in on the attention mechanism. That's a huge piece, but it's still just one part of a giant LLM.
That's the crucial final point to consider, absolutely. Attention is a major bottleneck, yes, but getting overall LLM energy down significantly still means you have to optimize everything else.
Like the big linear layers.
Exactly. The linear layers still do a ton of the work. So the really exciting next step, the potential here, is integrating this kind of analog gain cell attention mechanism with other in-memory computing techniques that are designed specifically for those linear layers.
So combining different IMC approaches for different parts of the model.
That's the path forward. This convergence of advanced memory like these gain cells and clever algorithm adaptation, it isn't just tweaking AI efficiency. It feels like it's fundamentally rewriting the rules, the economics, the very physics of how we run these massive generative models. It could potentially put powerful AI almost anywhere you need it, no giant server farm required.
And that brings us to the end of another deep dive into the world of generative AI.
Thank you for tuning in to GenAI Level Up. If you found this episode valuable, please consider subscribing and leaving a review on your favorite podcast platform. It helps us reach more curious minds like yours.
Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, keep learning, stay curious, and continue to level up.